Again, this is part B. We did part A last time. Use Newton's quotient. So Newton's quotient, we'll write it out again. It's the limit as h goes to 0. First of all, we can say f prime of x, our derivative, is the limit as h goes to 0. This is just your slope formula, rise over run. Your y values divided by your x values. Okay, again, if you think about 2 points here like this and making this h, well, this is plugging in x, so this point will be x comma f of x, and this point will be x plus h comma f of x plus h, because you're adding h to x. So their formula, or definition of a derivative, is just the slope formula. And looking at the slope formula as your run goes to 0. Now with that in mind, we have to plug things in. A little bit of work off to the side. Can you see that f of x plus h, I'll do that off to the side, would be x plus h cubed plus 1. That's going to be a little bit of work, right? Because you'd have to do x plus h times x plus h times x plus h. We could do it multiplying 2 of them and multiplying a third one. That's probably the easiest way to remember. Probably the shortest way to do this one would be, do you remember binomial theorem and using Pascal's triangle? This would have 4 terms, so it's going to equal x cubed plus 3x squared h plus 3xh squared plus 1h cubed, and then still plus 1 after that. So now I'm going to write that in for f of x plus h. X cubed plus 3x squared h plus 3xh squared plus h cubed plus 1 minus f of x, which is x cubed plus 1, all over h. Do some things nicely cancel out? Can you see that your x cubed minus an x cubed is going to go away? And your 1 minus a 1, those will go away. Ooh, I would lose a mark at this point. I forgot to write something. Can you see from step 1 to step 2 what I forgot to write? I forgot to write the limit part. So let's go in here. Equals limit. You have to write the limit part until you evaluate the limit. In other words, until you can plug in 0 for h, it needs to stay there. I can't plug in 0 for h because I would divide by 0. So again, I now have limit as h goes to 0 of, now if I look what's left, I notice that my 3 terms that are left on the top all have an h in them. So I'm going to factor out that h and leave me with 3x squared plus 3xh plus h squared on the top, all divided by h. This is nice because now my h's will simplify. Now I'm no longer dividing by h, so now I can apply my limit. I can plug in 0 for h, and I'm going to get this is equal to 3x squared. What we just found, the 3x squared, what does it mean? It's a formula for every single tangent line on x cubed plus 1. Graphically, if I draw this, this is Would you agree that that is x cubed plus 1? Okay? You would have the point 1 comma 2. If you drew a tangent line at 1 comma 2, plug in 1 for x into there, I would get 3. The slope of that line would be 3. Every single, if you wanted to find that here at 0, 1, its slope is, oh, it's not a very good one. Let me just cheat a little bit. There we go. Because I looked at my formula, and I was like, ooh. I have a formula for every single tangent line on the x cubed plus 1 graph, yes. And if you did this formula for an x to the 4 graph, you'd have every single tangent line on there, which is pretty amazing. So you get f prime of x is 3x squared. That's the tangent line for every single tangent line on x cubed plus 1. It is kind of cool. Terribly fascinating. Find the derivative of 5x squared minus 2x when x is equal to 2. In other words, if you drew 5x squared minus 2x, which is a parabola, and you took the point at 2 comma, in this case it would be 2 comma 16, and wanted to find the slope of that tangent line at that point, you would need to do the derivative. So how do we do these derivative questions? We start off with our definition of our derivative, that f prime of x is equal to the limit as h goes to 0 of our slope, f of x plus h minus f of x over h, and plug things in. Often I get people to do the f of x plus h off to the side. So I need to plug in x plus h into my function. Can you see that you would get 5 x plus h squared minus 2 x plus h. Wow. Let's move this over, make it nicer. If I simplify this, I'm going to get 5. This is going to be x squared plus 2xh plus h squared minus 2x minus 2h equals 5x squared plus 10xh plus 5h squared minus 2x minus 2h. Wow. There. Nice and small off to the side. Too small? Not done yet? Nice and big. It's 5h squared because that 5 would distribute and hit the h squared. Minus 2x minus 2h. Can I make it small? So we did that work off to the side just so that here we could write the limit as h goes to 0. F of x plus h we figured out to be 5. Oh my goodness, I'm going to need more space in that bracket. 5x squared plus 10xh plus 5h squared minus 2x minus 2h, bracket. Minus, and then here f of x, this is super easy because f of x was given to us. It's just 5x squared minus 2 all over h minus 2x. Every single time you use the definition of the derivative, nice things start to simplify. Can you see that the 5x squared and minus the 5x squared will go away? That a minus 2x minus a negative 2x will be plus 2x would go away. And what are we left with? 10xh plus 5h squared minus 2h. Another nice thing that happens is what you're left with all has an h. So what you can do with that is you can factor that h out, leaving me with 10x plus 5h minus 2 all over h. And that's our goal. Our goal is to simplify so we get rid of that h on the bottom. If we get rid of that h on the bottom, we can now apply the limit, plug in 0, and you get 10x minus 2. So what does that mean? Right? What did we find? We found a formula for every single tangent. What did the question ask us? Find the derivative of the function when x equals 2. So we can say when x equals 2, f prime of 2 is equal to 18. This means that the slope of the tangent of f of x equals 5x squared minus 2x at the point 2, 16 is 18. So all derivatives do, you get all excited about calculus, and it is, I'm going to say, it's super exciting. But it's a little bit of a letdown to find out that all calculus is the slope of a tangent line. You're like, really? You feel like I've been taking pre-calculus for 4 years to find out that? Yes, but its applications are crazy. Who would have thought slopes of tangent lines could do so much? Right? I mean, you probably had Newton on this high pillar all these years. That guy was amazing. That's all he found? That's it? But there is so much more to it. We're just starting the idea. But it's important that your idea always goes back to just that simple fact. All a derivative is an equation to find slopes of tangents. And you're like, we still have 3 units on this, Mr. JR? Yes. There's going to be like 3 units starting with this idea. All right. Question? So part of the reason why our unit isn't over in this second, because I've taught you already what calculus is because we run into situations where using the definition of the derivative is not necessarily easy to figure out the answer. So here's an example. Okay? We write out our definition of our derivative, that our derivative f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And off to the side, I'm going to switch colors. Off to the side, I am going to figure out f of x plus h. That would be 3 plug in. Oh, it's pretty easy to figure out. It's just 3x plus h. Make it a little bit smaller, put it off to the side. Now I can go back to my formula here and write limit as h goes to 0. F of x plus h is 3x plus h. F of x was 3 root x all over h. Oh. What didn't happen this time, like what happened with all the nice polynomial ones, Nothing canceled out. So we're going to have to use an algebra technique that you have used before, but I'm thinking you've forgotten. Or it's not necessarily going to come to you right away. But it has to do with square roots, and you used it way back in grade 11 in your square roots unit. Yeah, when you were in grade 10 taking the grade 11 course. Okay? Why do I do this here? This is just the definition. This whole thing is the definition of the derivative. F of x plus h minus f of x becomes your rise in your slope formula. No, that was an f that didn't, sorry. Yes. Yeah, my pen popped up. Yeah, that could be confusing. It was not supposed to be f prime of x. It's just an f. Thank you. Okay. So the idea that you're not thinking of happened when you got a question like this. You finished a long question with square roots, and your answer came out to be 3 over root 5 minus root 7. What did you have to do with that answer? Because if you left it like that, your teacher was like, I'm sorry, it's not simplified. You have to do something. Because you're not allowed what? Remember, you're not allowed square roots on the bottom, right? Yeah, there's a word in everything.
It starts with a D.
Close.
Okay, well, it's like
I will give you a hint. It does start with one of the alphabet letters.
Oh,
Yeah, I know. So, all right, I'll take out Q. You need to rationalize the denominator. Okay, yes, that starts with R. Multiply by what? You're going to have to multiply by 1. I like that. Okay. You have to multiply by magic number 1, which is not going to be 1 over 1. What is the magic number 1? So close. We have to rationalize the denominator by multiplying by, I'm going to put this one in brackets. Square root of 5 plus square root of 7 is the magic number 1. Okay? Subsequently, this is called the what of this. It starts with a C. That's the word I was thinking of. Not the complement. Conjugate. Whew. They use a nice English word that doesn't connect you at all, so it's the easiest one to forget. You are multiplying by the conjugate. The reason you multiply by the conjugate is on the bottom, it creates a difference of squares. What does a difference of squares do when you multiply them out? Right? What happens when you multiply x plus y times x minus y? You FOIL it out, and everything in the middle disappears, right? So you just get x squared minus y squared. Right? That's a difference of squares. Why is that so important with square roots? Because if I had the first one squared, my bottom just would become 5. If I had the second one squared, it's just 7. As a difference of squares, the bottom just would become 5 minus 7. Now the top has 3 root 5 minus 3 times root 5 plus root 7. So now we have square roots on the top, but on the bottom, things nicely go away. Using the idea of differences of squares, you can get rid of square roots. That's a connection back to when you were in grade 10, right? We're just going to make that nice and small like it was in your memory and put it over there. Okay? Right? Those facts are in your head somewhere. Sometimes they're really, really small. It's our job now to try to enlarge them. And sometimes that's the great thing about math class is you revisit an idea and you're like, oh yeah, I remember that. And so you're like, oh yeah, I remember getting that wrong. Yeah. Okay. So we have two square roots with a minus sign in between. In this question, I can get rid of those square roots if, put brackets around this one, I multiplied this by 3 root x plus h plus 3 root x. Can you see that that makes a difference of squares? But I'm not allowed to do that to a fraction if I just multiply the top. But I am allowed to multiply by fancy number ones. That is one fancy looking number 1. And at this point, if I had given you the hint earlier, oh, just multiply by 1. Yeah, you wouldn't have gotten it, right? It'd be like, thanks. So now what happens in our numerator? The numerator is a difference of squares. So as a difference of squares, it'll be the first one squared minus the second one squared. What does that look like? The first one squared, you see that 3 times 3 would be 9. And the square root times the square root would just become x plus h. Yes? When you multiply the first ones together, 3 times 3, that'll give you the 9. And a square root times a square root will square it, getting rid of the square root, leaving you just with the x plus h. Minus the second one squared. Well, 3 times 3, that will just be 3. And square root of x times square root of x will just be x. Over, and on the bottom, we could distribute that h, but I'm going to leave it factored out, because what's our goal? Our goal is to get rid of that h on the bottom. Yes. Oh, it should be 9. Yes. Thank you. Thank you. Minus 9x. Okay. So we kept the h factored on the bottom because it's our hope that we get something just with h's on the top that we can cancel out. Equals the limit as h goes to 0. Now, in our numerator, can you see if you distribute the 9, you're going to get 9x plus 9h. And then you subtract 9x. So after simplifying, are you okay if I just write 9h on the top? And on the bottom, we still have h times by 3 root x plus h plus 3 root x. And our h's nicely go away. We still have an h on the bottom. However, with that h on the bottom, if you plug in 0, what's the bottom going to equal? 3 root x plus 3 root x, or 6 root x? We're not dividing by 0. We're dividing by 6 root x. So we can now apply the limit. If I plug in 0, I'm going to get 6 root x on the bottom. And this simplifies to 3 over 2. The other reason that our calculus unit is a little bit longer, okay? Our goal is to find these equations, because what this equation is right here, this is the equation for the slope of any tangent line anywhere on the original equation, which was 3 root x. If I zoom out, view, Zoom, entire page. This was all the work we needed to do to figure this out, plus we had to remember about differences of squares and multiplying by the conjugate as a strategy from grade 11. Overall, if we counted how much time it took me to teach you this, we'll probably spend about 5 minutes on this question, okay? We are going to explore calculus to hopefully shave off 4 minutes and 59 seconds off of this question, so that when you get this question, you will be able to, in fact, you're going to go, okay, the derivative of this one is 3 over 2 x to the minus a half. Can you believe, first of all, are you okay with the square root of x being x to the half? And if it's on the bottom, I can move it back to the top by making it x to the negative half. The amount of time it took me to write that down will be the same amount of time that I will teach you so that you can do it that fast. That's another reason this unit takes a little bit longer than just saying, oh, derivatives are slopes of tangents. Yes?
I think I know how you did it.
Oh, well then don't tell anyone else. Keep that knowledge safely guarded to yourself to save time. Not for sure. How are we going to do this as a shortcut? Okay. The hardest thing you're going to find in this unit is once you learn the shortcut, when they ask you to go back and use the long method, I like to call it the long cut, shortcuts and long cuts. And you have to do this later. Yes?
But once you know the shortcut,
You can use it to verify your other answer. Yes. So like the shortcut in the one we just did, 10x minus 2, you can just sort of like, you will just be able to look at it and say, oh, it's common sense that the derivative is 10x minus 2. That's where we're going to get to in this unit. But right now, we're doing everything the long way. Find the gradient of this function at x equals 4. So we figured out our derivative to be this. At x equals 4, the derivative, there's that, at 4, oops, I wanted to write a 4 in there, is going to be 3 over 2 square root of 4. Square root of 4 is 2. 2 times 2 is 4. So the slope of the tangent line at x equals 4 on 3 root x is 3/4. Again, it's so nice to use your skills in graphing. 3 root x, would you agree that all that is your square root graph stretched? At 4, you would have the point 4 comma 6. This is the graph of y equals 3 root x. It's just your square root graph stretched by a factor of 3. And apparently, if you drew a tangent line to that point right there, the slope of that tangent line is 3 over 4. That's what we just figured out. Why is it 4 comma 6? Because if I plug in 4 into my original equation, my y value would be 6. So the graph is giving us a picture of what's happening. And we're figuring out the formula. By using the definition, we get a formula for every single tangent line. And then we can plug in an x value into that formula to find the slope. When you plug that x value back into your original equation, you find the original point. When you plug the x value into your derivative, you find the slope at that point. Oh. I'm going to show you function on your calculator. Go to math. Go to number 8, ndriv. If you have a new formula, it looks like this. So, the first part, d dx, notation-wise. That is the math short way to write, find the derivative of the following. So what did we want to find the derivative of? We wanted to find the derivative of 3 square root of x. That was our equation. And when did we want to find the derivative of that at? We wanted to find the derivative of that at 4. So what this function does is it says, I'm going to calculate the derivative at 4 of 3 root x. We already figured this out to be 3/4. So if I push enter, it should be 0.75. And it's 0.75, 0.00006. We have, okay, just proven that we are a little bit smarter than our calculator. Because the actual answer is exactly 0.75. But what your calculator does is it does a bunch of math over and over. It kind of guesses and checks, and it knows an algorithm to get closer and closer and closer. And eventually, it feels like, okay, I'm close enough. If you really put your calculator right close to your ear, you can actually hear it huffing and puffing from all the calculations it just did. It's like done a million calculations, and it got pretty close, but it didn't get exact. So we are able to find it exact and more accurately than your calculator. The best programming that's built into your TI-84 right now is not quite good enough. Of course, they're going to upgrade it, so you have to spend another $200. No, I'm just kidding. You don't have to. Save that money for Christmas presents for your math teacher. Okay. I'm kidding. So calculate the value of the gradient of f of x equals sine 3x squared at x equals 1. State your answer to 3 sig figs. So here we can go to our n derivative function. This is actually a good example because right now you do not have the algebra skills to figure this one out using the definition. So d dx of sine of 3, what was it, sine of 3x squared? 3x squared when x equals 1. Now, we might get different answers here. Make sure that your mode in all of derivatives are always based off radians. So when you get to trigonometric functions, it needs to be in radians. Mine is in radians. When I push enter now, I get negative 5.94. This would be an example of something they may ask on the calculator part of your exam. If they pick a function that you can't do easily using the rules we're going to learn, it could be quicker if you used a calculator. So this n derivative function is really nice. Yeah, here's another one. We won't plug it in, but this is an example of one that is extremely difficult even once you learn shortcuts. And if you tried to use the definition of the derivative of this one, you just probably have to cry. Doesn't take much anymore. It's like Pavlov's dog. I just come to math class and I start to cry.